Okay, good morning. We are going to work on the guided notes for systems of linear equations. Rather than try to go through each tutorial step by step, I figured it would be better to look at the guided notes, see the examples that are on there, and then go from there. If you have more issues or need more specific help, I'll gladly help you. But this way, I figured if we solve the problems that were on the guided notes, that would be a good start. So let's get into it. Here we go. So make sure you put your name on it on the top. That's awesome. We get the definitions to non-viable solution and constraints from within the tutorial. A system of equation is two or more equations that use the same variables. So in the tutorial, they use P and Q. P and Q for the total number of coins, the total number of pennies, plus the total number of quarters. They also use P and Q as the pennies and quarters, but in that situation, they wanted to know the value of the total for the number of pennies and the number of quarters. Those are the two different equations that use the P and the Q. A viable solution is a solution that is capable of working successfully within the parameters of the situation. If it's not even close, then it's not going to be a viable solution. Non-viable solution is one that's not capable of working. Constraints are the conditions that represented as an equation or an equality that the solution must satisfy, as in a number of p's and the number of q's must equal this number, or you have it must meet this value of the coins, like $101.57 as from the tutorial. So, um, so let's get into it. Write the objective. Write and graph systems of linear equations to determine the solutions. Graphing a linear system. The intersection point of a system of linear equation represents the values of the variables that make both equations true. So both. Okay. All right here. Okay. So the intersection point of a system of linear equations represents the values of the variables that make both equations true. The point of intersection, that's where the lines cross, like two roads cross at an intersection, is called the solution of the system. And solving a system means finding the location of that point. So we are going to look at solving a system of linear equations. Rewrite the equations in slope-intercept form. Y equals mx plus b. All right, let's see if we can get there. So let's see here. Okay, on to solving a system of linear equations. I'm going to go through this fairly slow because when we solve an equation, it's a little bit of a review. We need to work through the equation. This gives us a template, but it doesn't explain it exactly as well as I like to. When we have an equation, I highly recommend you get scratch paper to do this type of stuff on. We have plenty at the office, but you take the equation and we have to solve for the variable. So in order to solve for the variables, we need to simplify the equation. So the best way I can say that is to rewrite it, and then the goal is to get a single variable. In this case, we're going to solve for y. I mean, we know that because down here it says y equals, and we got to get that y all by itself. The way to do that is to isolate the variable. We isolate the variable by going through the following steps. So first of all, in the equation, after the equal sign, the 18 goes here. Then we're going to get rid of this x right here. And the way we're going to get rid of the x is by subtracting it from the left-hand side of the equation and adding it, or sorry, what you have to do to get rid of a variable or undo numbers is by doing the opposite. So right here, there is no minus sign in front of the x, so to undo that x, to get it over onto the other side, we have to subtract the x. They show that in a linear form by taking the x plus, or there's no negative sign in front of the x, and they subtract it this way. Because I do my math vertically, that 18 minus x looks like this. So I subtract it vertically to undo it, to get rid of it. And what you do to one side of the equation, you have to do to the other side of the equation. So that's how we got 4y equals 18 minus x on the line here. Now, so we got 4y equals 18 minus x. The next step is to get rid of the 4y. Well, 4y is the same as saying 4 multiplied by y, or y times 4. And so in order to undo a multiplication, we do the opposite. So we divide by 4 to undo that 4. So we're undoing the 4. We're undoing the 4 times y by dividing it. They show you that on here, and I'm showing you there. What we do to one side, we have to do to the other. I have to divide each term, the 18 and minus x, by the 4. So over here you see the 18, the x. Okay, now 18 over 4, or 18 fourths, reduces. You always got to try to remember to reduce your fractions to the lowest or the simplest form. So 18 divided by 2 is 9. 4 divided by 2 is 2. That's how we get 9 over 2 minus x over 4. So then what the system did, and I don't really understand exactly why, but they took this minus sign and brought it down and put it in front of the terms. And then they flipped the terms. So it's the equivalent of saying it's the equivalent of saying x over 4 minus 9 over 2 is the same as saying negative 9 over 2 plus x over 4. So it's the same as saying 3 plus 2 equals 5 is the same as negative 5 plus, or negative 5 equals, negative 5 equals negative 3 plus negative 2. I don't know if that was helpful or not, but essentially what they did was they made, instead of a subtraction problem, they made it negative plus. I don't know how to make that any more clear, but that's what they did. I tried to put arrows to show you kind of where everything is going and what's happening. Basically, it's just the format that they used. But it's a little difficult to understand how we got from 18 over 4 minus x over 4 to negative x over 4 plus 9 over 2. Subtracting a number is the same as adding a negative, I guess. We'll work on that. Okay, so that's as far as we got on this one. That one's a little confusing. I'm going to pause the recording and work the red side here. Okay, moving on to the right-hand side, 3x minus y equals 2. And we're going to go through the same process. We need to get it in y equals mx plus b, or slope-intercept form. And here we go. So we just write the problem out. 3x minus y equals 2. I subtract vertically. They did it horizontally. I'll show you that over on the left at the end. So we have subtract 3x from both sides. That's how we undo the 3x from the left side of the equation and put it over on the right side of the equation. We're left with negative y equals 2 minus 3x. That negative, remember the last one where they kind of flip-flopped it so that there wasn't a negative in front of the y? The best I can explain is that it becomes that. So instead of a positive 2 minus 3x, it becomes a positive 3x minus 2. So y equals 3x minus 2. That's your y-intercept form. Notice it looks like the y equals m. So in this case, the slope is 3 plus b. In this case, the slope-intercept is negative 2. Sorry, the y-intercept. The y-intercept is negative 2. And then I'll show you that over here as well. So we bring down the 2. We have subtract 3x. They brought it from this side here and put it over there. Same steps, just a slightly different way of working it out. I show you how I work it out and kind of how they got where they got. Because it's not always easy to follow the template. I really, really suggest that you work this out and practice these. So again, we got that weird flip-flop of the negative y and the minus sign here. And these two go in different orders because of that. All right, there you go on that part. Let's move on to number 2. Find the slope and y-intercept for the equations. This takes forever. Okay. trying to get back into this. It took me a little bit to try to figure out what was going on here. So they want us to solve for the slope and the intercept, sorry. So this is the slope and this is the y-intersection. So this is the slope and this is the y-intercept. Well, on mine, I have x and 4. But their answer key, the answer key on the guided notes has 1 and 4. I'm not exactly sure how we got from this negative x over 4 to negative 1 over 4. I apologize. I wish I did. But I'm not really sure. However, I did solve for the slope and got 9 over 2, and that goes here, 9 over 2. That's the y-intercept. That means if you selected 0 and 9 seconds on the chart, that's where it would cross the y-intercept. Okay, I'm going to get rid of all of this here. This section here, I'm going to hopefully pause and move, and then I'm going to solve the red side. Oops. Ah, no. Okay, I'm going to stop recording real quick while I'm messing it up. Okay, so what we're going to do here is we're going to solve for slope and y-intercept of this equation. So the first step is to copy over the equation to a workspace. We're going to get rid of the negative 3x by bringing it over to the other side of the equation. What you do to one side, you have to do to the other. We are left with negative y equals 2 minus 3x. Remember from the slope 1 over 4, I'm not really sure how they got the negative 1 over 4 instead of negative x over 4. And then in the other one where we flip-flopped the negative from in front of the y and made this the inverse of that. So it ends up being that negative flips over here. So it becomes 3x minus 2. So y equals 3x minus 2. Now, if slope is m, then our slope is right here. So that's 3. Okay? Bam. That's how we got that. This is 0 here, and negative 2 goes right there. Negative 2. So the slope is 3. That means it for every 3 up, it goes 3 over. That's slope. And then the y-intercept means it crosses the y-axis at 0, negative 2. Okay, number 3 asks us to plot the graphs and find the solution to the given system of equations. When we plot the two equations, the two lines intersect at. Okay, so where do they intersect at? So I'm following this highlighted section here. That's right where they cross. I have to figure out what that coordinate is. We have the x-axis and the y-axis. Oops, wrong way. So we start here on the bottom and we go over to the 2 because this is over 1, 2 to get over here. So that brings us up to the 2 on the x-axis. And then we know we're going to go up to the 4 on the y-axis. So we're counting it. So we have 2 there, 4 there. The x-axis coordinate is 2. The y-axis coordinate is 4. So x equals 2, y equals 4. Oops. Delete that. Let's say that actually equals 4. Okay, there we go. Okay, on the next one, the next question they want us to do is look at this. Plane A is descending toward a local airport at the rate of blah, blah, blah. It gives us all this, like the word problem. And then we see the X represents the time in minutes and Y represents the altitude in thousands of feet. So the X is down here on the bottom. And so this is the x-axis, and it is in time in minutes. So next to the x, it says 10, 9, 8, 7, 6 under here. So then it goes 1, 2. Okay, so this is a 2 right here. That's a 2. Now, what we're going to do is we're going to move the ruler to see where that spot crosses right there. So it goes from a 1 to 1 to a point, or sorry, 0 to 0.5 to 1 to 1.5, and then it's in between the 1.5 and the 2. There's the 2, there's the 1.5. It's right in the middle, which makes it 3/4. Or, excuse me, I misspoke. 1 and 3/4, which is also written as 1.75. So 1.75 seconds. So in 1.5 seconds, right here, this line both cross right there. Now, in elevation, altitude, it's measured in thousands of feet. So it says 1, that's 1,000, 2,000 feet, 3,000 feet, 4,000 feet, 5,000 feet, 6,000 feet, 7,000, 7,500, and it looks like it's in between 7,500 and 8,000. So we say it is at the 7.75 mark, 7.75 mark, and the altitude at 7.75 actually is 7,750 feet after approximately 1.75 minutes, or 1 minute and 45 seconds. There's a little conversion there. 1.75 minutes is the same as 1 minute and 45 seconds. 0.75 is 3/4. 3/4 of a minute is actually 45 seconds. Think of your clock. Think of it broke into quarters. This is 15 minutes, 15 minutes, 15 minutes, and 15 minutes. So now we have 15, 30, 45. That's how we got that 45 right there. Okay, gonna pause and move on to the next problem. Okay, the next page starts with determining the number of solutions in a system. When the graph of a system of equations produces parallel lines, and refresh your memory, parallel lines are two lines that go on forever and they never, ever cross. They don't cross. They just keep going along forever. They stay perfectly the same distance apart on both ends. That's parallel. That means the two lines will never meet. Meet me in the middle. Okay, if there is no coordinate point that lies on both lines, there is no solution. So remember, the solution is the intersection where they both meet. If they never meet, there can be no solution. When the graph, so there's no solution. No solution. One solution, when the graph of a system of equation produces intersecting lines, there can be only one solution, right? It only crosses the two lines, only cross at one point. Only one solution. The coordinates of that point represent the single solution to the system. Not bad. Infinitely many solutions. Itty bitty living space. Sometimes the two equations of a system produce lines that overlap each other when graphed. This means that any point along, that means every point along both lines is a solution. So we have the line and the equation of the other line, they go da 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 da, right? So you get the chart, you get the line, you get the other line, and they overlap. If they overlap, every point where they overlap is a possible solution. Gonna pause again and move on to the next one. For the next part, they want you to take what we just talked about as far as looking at the lines and looking at whether there's a number of solutions. So here is a system of equations. Here is where they meet. They cross right there. So that means that there is one solution. Next, we have the two lines that are parallel. We can't see that they're parallel, but that's what they're indicating. So there is no solution. Next, if we scroll down just a tad, we see poorly here that this is a red line and a blue line on there. That's supposed to be straight. There you go. I made it straight on accident. So that means there are an infinite number of solutions because the red line and the blue line overlap. All right. Okay, I'm going to go ahead and pause and move on to the next one. All right. So the next page is page 4, I guess, and it's called Modeling with a Linear System. So essentially, I think what they're saying is that you have a word problem and you can model it to solve it by using equations. All right, so check this out. Whenever I have a big word problem, I always highlight the points, right? Like whatever seems like it might be information that's worth needed. And then I start going through the questions. To create the two equations, use the standard form for linear equations. So that's just like x equals or y plus x equals. You know, it's just the standard equation form in a straight line, linear. So let x represent the number of blank answers. Well, on here it says the very first one says 100 points for each correct answer. So, and then, so we put x represents each correct answer and y represents each incorrect answer. Now, it doesn't talk about what c equals, but c equals the total number of points, right? And we know that because down here it says 500 points afterwards. So, okay, the first equation is based on the number of points Kimberly has earned. Correct answers give her 100 points. So that means in here, this x is multiplied by 100. Bam, goes right there. Oh, is it going to take out all my answers? Oh no, it deleted the rest of my answers. Okay, so it's going to be a hundo right here. I'll fix it real quick. Luckily, I did this ahead of time. All right, see how we got all those pieces? Okay. I gotta switch this to red because that's the way I did it in my head. Okay, incorrect answers reduce by 200 points. So reduce or subtract minus 200. Now this 100 is still there. We didn't change that. So 100x plus negative 200. So just out of clarity, it is and, that's the plus, loses, that's the minus 200. Okay? So that's the and, you minus 200. Now, add a negative, cancel out, and it's the same as subtract 200. I have $100. I add owing somebody $200. So that's I add a negative 200 is the same as saying 100 minus 200. So, oops, I didn't mean to do that. Let's go back. I want it to be blue. Why? Because I said so. Get my cursor action back here. So 100 minus, or sorry, 100x minus 200y equals, and then we know that it equals 500. Okay, so then that's how we figure that out. The second question is based on the number of questions Kimberly has answered, which is 20. So we have X. Let me do this. Highlight. We have X. Bam. And then we also have the Y. Bam. Equals 20. So we know that it's X plus Y equals 20. X being the number of questions right. See, X is correct, and Y is the number incorrect. We don't need to know whether she got them incorrect or positive. Correct or incorrect. We are just adding the total numbers answered. So you might answer 5, but only got 4 correct, but you still answered 5. That's this. So that's how that works. And then you have to check them for viability. So what you're going to do is go back and double check that it works. I'll pause and get onto that next. Okay, the last section on page 4 talks about checking for viability. This idea that we're checking for viability is kind of the most important thing you can learn in all of math. If you are making a business transaction and somebody says to you, hey, if you give me 2 of your 20s, I'll give you 4 of my 10s. You got to stop and you go, wait a minute, 2 for 4? That doesn't sound right. I'm trying to make change. I need some 10s, but I already had 2 20s. They want to give me 4 10s. That sounds like a good deal. All right, let's exchange. But likewise, you don't want somebody to say, hey, these 5 nickels are worth way more than your 2 quarters. Do you want to trade my 5 nickels for your 2 quarters? No, that doesn't make sense, right? And we don't want you to get schnookered, as the word is. We don't want you to get cheated. We don't want you to get the short end of the stick. So you want to make sure that the solution or the answer to your problem makes sense. So viable solutions need to make sense in the real world situation. Many items can't be represented by whole numbers. For example, you don't have 2.5 children in your family. The average household has 2.5 children, but that means someone has 3 and someone has 2, and it averages out to 2.5. So those answers that are not realistic are called non-viable solutions. Non-viable means it's not gonna work. If 2.5 eggs out of 10 die, well, then the reality is 3 eggs die, but that's not a solution because you can't have a half. So when representing a situation, these equations are called constraints. That means both have to be true in order for the solution to work. Constraints. Think of those as the gutter bumper things that protect the ball from going into the gutter. Okay. You can only knock down 10 if you stay out of the gutter. These constraints make it to where you get down to the end to get the correct strike. I don't know. Bad example, bad analogy. Okay, the last page, 5 5 out of 5. We're now going to start working through the practice here. Again, my first step is I go through and I highlight what I think is the important stuff out of the problem. Again, you don't have to do that. It's probably not easy for you to do that, but that's what I do when I'm working out a word problem is I highlight or circle those. So we got 35 tickets. Stephanie, 5 tickets for a game, and rides cost 7 tickets. And then if she does 8 activities, I guess that's some number of rides and some number of games, totaling 8 activities. So we take the game, right? And it says let X represent the number of games she plays. So it says there's 5 tickets per game. So each game requires 5 tickets. Let Y represent the number of rides she takes. So each ride requires how many tickets? 7 tickets. Yes. Okay, so the equation becomes 5x, as in 5 tickets times each game, plus 7y, or 7 times the number of rides she rides. And she only has a total of 35 tickets. So it can only equal a total of 35 tickets. I'm going to pause and make this little chart and kind of show you something. In earlier or other types of graphing type lessons and or problem solving, we might need to do a table like this where X is still the number of games and Y is the number of tickets, but we know that the number of tickets spent on games plus the number of tickets spent on rides equals 35. So one game plus 5. Sorry, I misspoke. Let me rewind. One game is 5 tickets plus one ride. That's supposed to be a 1 right there. Let's see. So one ride. So one ride plus one game is a total of 12 tickets. That does not equal the 35 that she has available. So we could say 2 times 5, which we know is 10. Okay, I can't do the mouse for that. I don't know what I was thinking. So that equals 10. And we could do 2 times 7, and we know that equals 14. 10 plus 14 equals 24. Okay, still does not equal 35. We could do 3 times 5 is 15. 3 times 7 is 21. 15 plus 21 is 36. Oh man, we're too high now. Here, too low, too low. Now we're too high. So we would sit there and we could guess and check, guess and check, guess and check. But using the equation to solve for it is going to be a lot clearer. Plus, there may be more than one solution. Okay. To this one anyways. Next, we're going to go on to write the equation representing Stephanie's participation in X number of games and Y number of rides. Stephanie wants to participate in 8 activities at the fair. So let's work that out. Okay, one of the last problems here, it says write the equation representing Stephanie's participation in X number of games and Y rides. Stephanie wants to participate in 8 activities at the fair. So just as I did before where I made that like T chart to see if it worked, I'm doing the same over here. The equation to participate in 8 activities becomes X plus Y equals 8. The number of game activities plus the number of ride activities equals 8. It also says here using the smallest number of tickets. So we're trying to do the math with the smallest number of tickets first. So because we know that there are, if we had 8 activities using games, because games use 5 tickets and rides cost 7 tickets, the fewest amount of tickets with the 8 activities would be all 8 games and 0 rides. But we know that that does not equal 8. Or sorry, does not equal the same number of tickets. So 8 activities using the least number of tickets is going to actually be 8 times 5, 5 tickets per activity, per game, sorry, 8 games, 8 is our 8 activities equals 40. But we can't do that because we only have 35 tickets. That's in the rules, that's in the constraints, if you will. So that one doesn't work. Now, Stephanie would only play games. And because each game, I'm kind of backtracking here to fill this in. Each game, it requires 5 tickets. So the smallest number of tickets she could use is 5 times 8, which is 40. We just did that. But this is, oh, I don't want to zoom in. I want to, sorry, folks. So 5 times 8 equals 40, but this is 5 more tickets than she has. Oops, let's go back. 5 more tickets than is available. Checking this boundary, we can see that Stephanie's plan has no viable solutions. Oh, darn it, Bobby. I don't know why it's not writing right there. I got out of my writer deal. Why is it not writing while I'm trying to record? What did I do? Really? Did it lock up? Did it freeze? Did I die? Oh boy, let me stop recording. Okay. This isn't necessary to follow these steps, but in order for this last part, checking this boundary, we can see that Stephanie's plan has blank viable solution. This means blank numbers exist that satisfy both equations. We're going to go through this table basically prove our answers. So as we did 8 activities, which would be if we started with 8 games and 0 rides, still 8 activities, but it ended up being 40 tickets. So I went through the entire list from both possibilities, and I'm not going to do all the math worked out, but 7 tickets, 7 times 5 is 30. 5. 7 times 1 is 7. 35 plus 7 is 42. And by the way, that one up there was 40. This one's 42. With 6 times 5 plus 2 times 7, that equals 44. 5 games and 3 rides would be 46. 4 games and 4 rides would be 48. Notice that it's switched now. There's less games and more rides. We know more rides is going to be more tickets. I just did this because I wanted to finish it out. So 3 and 5 is going to equal 50. 2 games and 6 rides is going to be 52 tickets. So sorry for that. 1 game and 7 rides would equal 54 tickets, and 0 games and only 8 and all 8 rides would be 56. So essentially this one, and proved by going through this step, since none of these options are 35, none of these ways of only doing 8 activities uses all 35 tickets. So she cannot do 8 activities with 35 tickets. So it has no viable solutions. This means no numbers exist that satisfy both equations. She cannot do both. Okay, and then we need to complete the summary. The gist of the summary is, why do we use systems of linear equations to model real-world relationships? Well, a system of equations is easier to solve than to do these guess and check tables. And we need to do more than one single equation because sometimes the questions are slightly different. One question might ask, how many pizzas do you need for the students? And the other question might have, students that are freshmen and sophomore need 5 pieces. Students that are juniors and seniors need 6 pieces. So they're 2 different problems, and that's why you need a system of equations. All right. I hope this helped. I'm going to post the video. If it doesn't, please feel free to give me feedback. Thank you and have a great day.